Um, all right, so good afternoon, and you're welcome to uh, today's class. So the class is a continuation of where we stopped last time, right? So we'll just do a little bit of recap, then we'll move on as quickly as we can. All right. So class rep, I think we stopped at page 22, right? Yeah, I think we stopped around here.
Yes, sir.
This is where we stopped, right?
Yes, sir.
All right, so we can continue from here. So last week we looked at the basics of finite state automator, right? And we looked at the basic operation of the finite state automator. Please, at any time you cannot hear me, let me know so that I can quickly readjust. Yeah, so we looked at the basic, the internal working of finite state automator. We looked at how we could define it formally. Now, we said that the formal definition of finite state automator is to remove any form of ambiguity from its operation. For instance, when we define when we look at the number of strings or the kind of string or the kind of language or the kind of grammar that a finite state can accept, if there are ambiguities or we don't know if the automaton or the machine can accept a certain kind of language or certain kind of symbol, that can be put to rest by just looking at the formal definition. In the formal definition, we have what is defined as a set of inputs. We look at what is defined as a set of states. We looked at what is defined as transition function. We looked at the initial states, the accepting states, and a host of other things. So once we're able to look at all this, it sets aside all confusion as it relates to that automaton. We also went further to look at the representation of a finite state automator in table form, right? And in the diagram, in schematic form or diagram form. So I think we're able to look at the conversion of maybe some FSA or finite state automator from their table form to their diagram form and vice versa. Of course, we looked at FSAs as being in different forms, right? So towards the end of this slide, we're going to look at the classification of FSAs. So we have the Moore machine, and we define the working as being as there's an output upon a transition from one state to the other. For the FSA, we have that there's a transition. Then we say that we use a double arrow to represent accepting state or final state. So accepting state is for languages being accepted. So if a language is accepted, we say that if the number of strings on a particular character or a particular symbol is passed through a particular FSA from the initial state and it arrives at the final state, we say such symbol or sub alphabet is being accepted by that FSA. So this is a regular milling machine where we have the initial states. These are our initial states, right? Being represented by an arrow pointing at it. right? And we have the input and the output. So this 0 is the input, this is the output. So it is read that once you are at A and upon the receipt of 0 or upon reading 0, you move to B or you transit to B and you output a 1. So if you are supposed to represent this story on a table, you say you're at A, you receive a 0, this is 0, you move to B and you output a 1. That's how it is read. You are at A, which is the initial state, you receive a 0, input 0, you move to B and you output 1, which is still under 0. Now, if you are at A, you receive a 1. Now you are at A, you receive a 1, you move to C, and what is the output under 1? It is 0. So those are the things we looked at very clearly in the last class. Then we also looked at for the Moore machine, which has its output on the state. So the output is not dependent really on transition. So we say you're at A, you're at A, no, sorry, you're at A, this is A, right? You receive a 0, you move to B, you receive a 0, you move to B, you are at A. Okay, this is a regular FSC. You are at A, you receive a 0, you move to B, you are at A, you receive a 0, you move to B. Now, one thing is a bit looking confusing on this diagram. Of course, you can see this one here, you can see another one, and here you can see another one. Oh, sorry, that was a mistake. Let me clear this one first. So you see this one here, you see another one, here you see 0, and here you see 1. Now, these are not part of the input transition. However, they are only telling us that this state is an accepting state. You remember last week we said that all accepting states are represented by what? A star, right? And non-accepting states are not given any value. However, to further illustrate it, all those ones giving stars are represented by 1, and those without stars are represented by 0. So when you look at this diagram, this table here, you see that A is an accepting state, is giving a star. B, or an asterisk, sorry. B is an accepting state, is giving an asterisk. C is an accepting state, is giving an asterisk. D is not, so there's nothing written in front of it. However, for further processes, for you to do any computation with it, all those that are assigned with asterisk are given the value of 1, 1, 1, and those without asterisks are giving the values of 0. So these are not outputs in any ways, they are just symbolic to tell you that, okay, this is an accepting state, this is an accepting state, right? Showing that, okay, A is an accepting state, B is an accepting state, C is an accepting state, D is not an accepting state. And again, this here is showing us that A is an initial state. I hope you understand up to this point. You understand up to this point. All right, so no response, so we'll move on. So let's now look at Okay, there's an individual who has raised up his hand. Yes, you can speak, Lawrence.
Yes, sir. So, from what you explained, I understand what you said about the regular FSA, but I think I missed the part on more machines.
What
I
did you
don't.
miss there?
You were saying that the output is dependent on. I don't. I did not get that, sir. You said something about the output being dependent on. That was the part you said something about output being dependent on something. I can't
Yes,
remember.
we discussed that last week, and I was just doing a recap. Okay, so let's look at it. Um, so this, now you see this is a milli machine. Wait, I want to look at this. So this is an example of the movement of a milli machine. So this is a state A. This is a state A, right? This is the input. This is the output. So say the output is written beside the character for each transition as follows, right? He said this indicates that if the machine is in state A and receives input 1, then it outputs a 0 and moves to state G. So what we are saying is that for milli machine, its output is dependent on transition. So for there to be any output here, there must be a transition. So you can see it is at the transition state here that you get an output. So that's for a milli machine. So when you are state A, upon the receipt of an input 1, you move to state G and output is 0. That is for a milli machine. However, for a more machine, there's a slight difference. Now, this is a more machine, right? So what a more machine is that you are at a state. Upon the receipt of this, you can see at this side, there's no output by the side. There's no output by the side of 1. So that means the output, which is on G here, is not in any way dependent on this transition function. But for milli machine, the output is dependent on, upon the receipt of a particular value, then you output something. Do you get that?
Yes, sir. Yes, sir. Thank you, sir.
Okay, so let's move on. What is this? So moving on. So, of course, this is still the example of a milli machine and the table, and we explained how this table works. I'm sure you still remember how the table works now. I'm just doing a form of recap. Say you at A, you receive an input of 0, you output 1, and you go to B. I'm sure you are still conversant with that, so I still explained that this morning. So this is for a more machine. You are at A, you output 1, you are at B, you output 1, C, you output 1, D, you output 1. However, for the table, it says you are at A. Upon the receipt, let me use this annotation. So you are at A. Upon the receipt of 0, you move to B, right? So what is the output of B? So you go to B and put the value here, 1. Then you are at A. You receive a value of 1. You go to C. What's the output at C? You go to C, this C here, you put your 1, right? So you are done with A. So you are A, you receive a 0, you remain in B, the output of B is still 1. You're at A, you receive a 1, you move to D, the output of D. So you go and look for D, the output, you put it here, 0. That's if the table is not all drawn up. Then you are done. So when you're at C, you receive a 0, you go to A, then at A, what's the value? 1. So, and you continue like that up until the table is complete. Okay, so okay. So I think I've explained why you have these zeros here. This one is not input, they are not input functions. They're just signifying that these are the values assigned to each of these accepting and non-accepting states. That's what this signifies. All right, so moving forward. So there's a concept called the black hole, right? Oftentimes when we draw some, when you draw some finite state automators, you will come across some that do not have any inputs that can make it go anywhere. For instance, let me draw something here. Now you have A, you have state A, right? And let's assume state A is the initial state. Now state A, maybe this is B, goes to B on 0. But when you now inspect, you find out that there's no other way, there's no state leaving B, leaving A on 1, right? So this doesn't exist. What it means is that once you have finished drawing all your diagrams and everything, you find out that when you draw the table, you find out that this is A, right? Under 0, you go to B. Under 0, go to B. Under 1, there's no way you are going. So what intuitively, what we are saying in essence is that if this phenomenon occur, actually under 1, A is pointing to a certain state called the black hole state. Do you get the explanation? You understand what I've just explained? Okay. All right. Thank you, Lawrence. So with an FSA, we often arrive at a situation where we can reject the string without needing to see the rest of it. For example, if you have an acceptor for the language 1, 0, asterisk, we can reject the string 1011 010 like that as soon as we read the fourth character. Beyond this point, we don't care what we read. The fate of the string is sealed. The most convenient way of dealing with this is to have a special state that represents rejection before the input is complete. The transition coming out of such a state should lead right back again. Therefore, once the machine gets into that state, it can never get out. For this reason, it is sometimes known as a black hole. By analogy, with this, with those regions of outer space with such a high concentration of gravitational pull or force that nothing that enters there ever escapes. Now, this is representation of a black hole. Anything that is getting inside of it here, once it gets in, we have to force it to remain there perpetually, right? We have it. Who is that one disturbing? Yeah, G-Boss said, please mute yourself. Yeah, so we have it perpetually going inside the a black hole perpetually. So we're going to see a clear example of that in a bit, so that we could have a clearer understanding of what that is all about. Right. So going forward, so a typical FSC will have a black hole. Only one is ever necessary, with many transitions going into it. To exclude the black hole in a state diagram with all these ancient arrows, we make the diagram looks excessively clustered. For this reason, we generally omit the black hole from state diagrams. Therefore, when there is no arrow, now look at the definition. When there is no arrow emerging from a state for a particular input character, now input characters can be zeros or one or two, or depending A or B, depending on the input character you have defined, it is assumed that there is an invisible arrow leading to the black hole. And of course, the black hole is never an accepting state. So please note, take notice of this, that the black hole is never an accepting state, right? So this is an example. So design an FSA to accept the language consisting of a binary string that begins with 1011. In other words, begin an FSA, design an FSA for the language given by the regular expression this. So that means, look at the diagram to make it quite simple. Let me use a notation. Now, what this is telling you is very, very simple. We are supposed to design this as the basic, and any other thing we have to end inside that. Upon the receipt of 0 or 1, it will, as much as it has, it must remain on that last state. So you have the initial state A, right, which is here. It is now the input you start looking at to move from state to state. You have, upon the receipt of 1 at A, you move to B. When you receive the next one, which is 0, you move to C. When you receive the next one, 1, you move to, from C, you move to D. From D, you move to E. Now, look at it here. You have what you're supposed to test: 1, 0, 1, 1. You're supposed to design a finite state automator that can that can accept this. So in essence, as soon as it reads this last one, it should be in the accept state. So this is the accept state. Now it now says that once you are the accept state, on the accept state, once you receive any input again, you must force yourself to remain at that point. So in a way, as simply as it is, if you cut off all this, let me clean up so that we see. When you cut off all of this, the simple diagram you're supposed to draw is just here. That's just all they are supposed to draw. However, because of the concept of black hole, you have to look at the other options that could come on each of the states and force it to a black hole. So you have A, you already have 1. The second state is input possible is what? 0. So you force it to a F. This one you already have 0. The other input is what? 1. You force it to F, a state F, which is called the black hole. Then here you already have what is emanating from it? 1. The next state that can emanate from that can leave it is what? 0. You force it to black hole. Here you have 1. The other state is what? 0. You force to black hole, and like that. Right? So that is as simple as it is. So you now force that black hole to also remain perpetually here as soon as anything gets into it, as seen in the previous diagram. Sorry. Seen as seen here. Here, you can see this. You force the diagram to perpetually remain here. So you see any input coming from it, coming towards it, then when those inputs get towards it, it must be forced to remain here permanently without any form of escape. Do we understand the concepts? Do you understand this concept quickly? Do you understand? I don't think there's any response. Or have I been logged out? No. Oh, okay. Why are others not participating? Or they are just playing somewhere? Okay. Okay. So you can unmute yourself and speak. All of you now. Let's see who is not in class or who is on the highway. Yeah, you can unmute yourself.
Understand, sir. Wait, I understand, sir.
Yes, sir.
Understand, sir.
Some of you are even sleeping, sir.
Yeah, I understand, sir.
Okay. All right. So we can now move on from this point. So you see, the state F is clearly acting as a black hole. Therefore, we can simplify the diagram by deleting it. So you can see there's one F that was going down from here before, right? All these ones were coming into it, coming into F, right? So we can simplify it by just clearing it off. And the basic diagram we're supposed to draw is this guy. So when I say you should draw a diagram for an FSA, right? You could have it drawn in this manner and introducing the black hole. Then you could go ahead to now delete the black hole eventually. So it depends on what is needed or the instruction given. But so if I give you maybe 111,001 and I ask you to draw an FSA that can accept that, I'm sure you should be able to do that now. So any transition that are not shown are assumed to lead to this black hole. Another simplification is to combine arrows that starts and finish with the same state. So here, when you look at this, you have that A, that's 0 and 1, being forced to remain here. So you can see you have 0, 1, not 0/1. Though some textbook may use 0, 1 as being representative of this, but for this course, we're going to be using 0, 1 to tell you that you have two inputs entering into that. So this is for 1, this is for 0. So we can put that 0, 0, 1 getting into state. So just use one arrow to represent it instead of us to make the arrow very cumbersome, right? So that's what we'll be using going forward. So so note, don't confuse the 0, 1 notation with the 0/1 notation that we use for Mealy machine. Some books use 0, 1 in such situation, so there are some dangers of confusion. For us, 0/1 means read 0, write 1, or output 1, while 0, 1 means read either 0 or 1. So note that E here is not a black hole because it is an accepting state, as we have earlier said that a black hole is not an accepting state. Yeah, is that fellow disturbing? All right, so we omit a black hole in a state diagram but it must be included in the states table. Now, why we have to branch to Blanco is the concept of equivalence, reduction, and also removing inaccessible states. That's why we have to visit it earlier. So I have to divide this class into last week and this week for you to get at least a bit of understanding of it, because by the time we get to the next one, it's going to be very fast roller coaster. So, of course, we have looked at what milling machines are and what more machines are. So generally, FSAs automators can be classified, can be looked at as acceptors, classifiers, and transducers. So acceptors, an automaton that computes a Boolean function is called an acceptor. All the states of an acceptor is either accepting or rejecting input given to it. Classifier, on the other hand, has more than two final states, and it gives a single output when it terminates. Transducer, on the other hand, is an automaton that produces output based on current inputs and or previous states. Is called a transducer. So transducer are two types, which are milling machine and Moore machine. So we have seen the working of the milling machine. We have seen how Moore and milling machine works generally. So what are the applications of that's when you say DFAs, determining finite state automators, right? So automators can be classified into two, which are deterministic finite state automator or non-deterministic finite state automator. So for deterministics, whereas DFA can be implemented as a table-driven or hand-coded scanner, right? So automaton or finite state machine can be implemented as a lexical analyzer and a host of others. So that's what we have for here. So you could have a lexical analyzer converted to a non-deterministic finite state automaton, then converted to a deterministic finite state automaton, and implemented in a form of table-driven. So, however, most commercial and open source compiler use hand-coded scanner. Such scanner is faster than a generated scanner because during implementation, some overhead that is necessary in a generated scanner can be removed. So when writing a hand-coded scanner, usually there's no need for the explicit conversion of the grammar or regex to a DFA, since it is possible to implement the scanning algorithm manually directly from the lexical specification. Well, I just put that there for you to look at some of the application and explanation of the use of scanners. So if an accepting state has been encountered, the scanner rolls back its initial state or its current character position to that point and reports success. Otherwise, it reports an error. So those are the basic application of the DFA, which is the finite state automaton. Yeah, just in a bit, we just take a few minutes break and we move to the next chapter so that we could have better speed. So we could have a 5 minutes break while yeah, I hope you can see my screen. Yeah, can you see my screen?
Yes, sir.
All right, so just let's have about 4 minutes break so we could start the next class. Yeah, so I hope you are well rested a bit. Can we continue? Yeah, who is this? Who happy, whatever. Oh, wait, Philip. Who asked you to write your name? Oh, sorry. I think I'm mistaken. Can we continue, please? Oh, can you still hear me? Can you hear me, please? Okay.
Yes, sir.
Okay, so let's continue. So we're just going to be building up on what we have learned so far, but I think it is important to pay very close attention at this point. So if you're in a place that you are not comfortable or it will steal your attention, just leave that place and please pay attention and get it once and for all. I think this is important. So we want to look at a concept called um, equivalence and reduction of a finite state machine. We're going to be looking at some processes, but before we look at that, we need to introduce ourselves to a bit of theoretical background on this. So moving forward, we said equivalence machine. So if you and an individual have decided to write a computer program independently, right, to perform the same function, it's almost certain that the programs that you have written will not be the same, except probably you do, right? So nevertheless, it is quite common to come across two quite different machines that behave identically. Now, identical behavior lies behind the concept of equivalence. So equivalence means that though you are different in nature, but you function in some certain ways that are quite similar. Is that one disturbing the class? You function in such a way that are quite similar. So two finite state machines are considered to be equivalent if they produce the same output for each input. Let's read that again. Two finite state machines are considered to be equivalent if they produce the same output for each input. All right. So two finite state machines are equivalent if they have the same input alphabet. And for machines that output strings, the same output alphabets. And if for every input string, the two machines produce the same output, such machines are said to be logically equivalent. So, what brought about the concept of equivalence of machine? So the concept of equivalence raises two questions. Firstly, how can we tell if two given finite state machines are equivalent? That's the question. Even though their alphabets are finite, there are infinitely many possible input strings because an output string can be arbitrarily long. We cannot possibly test them all. Right? So the first question is, how can we tell if two given finite state machines are equivalent? The second question is, it concerns efficiency. If you build a 100 state machine that is equivalent to another person who has developed a 1000 state machine, then we may assume that yours is clearly efficient. However, we cannot say that categorically. Because if you have, for instance, something that maybe you are developing a machine that is life critical. We permit redundancy. We should allow redundancies to coexist with the main. That you should have what we call redundant nodes that can help you when there is a problem or when there is maybe a fault detection, so you can shift the load from the main node to other nodes that you feel okay can work. A good example is that the popular Lagos Ibadan Expressway that has defied all solution presented to it for so long. So let's assume that instead of having to follow the Long Bridge or Kara Bridge, there is another route that you can use to link maybe the interchange from Abeokuta to Ijebu. You could have another route which is still maybe parallel to that of Lagos Ibadan Expressway. Let's assume that you can still have others, though it will cost the government a lot of money, but on the long run, they would have been able to do something very spectacular, and that is making Lagos accessible to as many people as want to add value to Lagos. And again, the congestion that you have in Lagos will be greatly reduced. For instance, an individual can be working in Ijebu Day and be coming to work in Lagos because he knows that, okay, if he leaves his house by maybe 6 a.m., by 7, he should be in Lagos. Some people can be living in Ibadan. So the cost of accommodation will be greatly reduced in Lagos, right? So though nodes at times may constitute redundancy, but they cannot be wished away in any form of construction. So we assume that yours is clearly more efficient. So if the logic of the machine had to be incorporated into mass production, to mass produce microprocessors, then your design will save the company more money. That may not be true all the time. What about if all the 100-state machines, they are really they are the core working microprocessor, and one of them fails, and unfortunately, if the one that fails is the most critical, that means that system is grounded. But if you have some other redundant microprocessor that could work in similar ways as that system would have worked, then you still continue working while you try to look for a way to fix your system. So the second question is whether we can take any finite state machine and improve it by some routine processes until we obtain the most efficient machine possible that does the same work, right? So the question, let's give maybe an example that you can relate with easily. Let's assume that we have, I think most of you have started taking up employment now. Instead of the company you are working with to pay a full graduate or a full stack developer that is a graduate, he has served, they prefer to just pick you in and be grooming you until you become so good as the other fellow who is just a graduate, but paying you less. So this, what are the steps that they took you through in order to make you at least good enough programmer to replicate the work that the other individual would have done seamlessly? So we're going to be looking at these processes. How can we convert one finite state machine to a better one that is similar to the more sophisticated ones? I'm sure you know that some of you who use iPhone now, most of them are from China, right? The original ones produced in US are quite expensive, or in the UK, they are quite expensive. But an imitation is what most people use here in the country, right? And they find it cool because, one, it is cheaper to buy, but it does the same function, right? So we have China products, and then we have German products. So what you put at the back of your mind is that once you are using a Chinese product, maybe 3 years, if you are using a Chinese car or all those funny cars, 3 years, you know that you start having problems. In those days, we could have, there's this bucket that we used to buy then. It could last several years, but how many days can some of these buckets that you use now, how many days can they last? All right, so moving forward. So given any finite state machine, M, we can carry out two processes on it. So those are the processes that we could use on that machine to make it fit, or that make it equivalent, or that can make it do the work of the other finite state automator. So the first step is called the reduction process. Yeah, which produces a reduced machine that is equivalent to M. The second process, called standardization process, relabels the states so as to put the machine in a standard form. So let's quickly look at it. So the reduction process starts with removing of inaccessible states. So the first stage is in the reduction process is to remove any states that can never be reached. Of course, we just concluded our thoughts on black hole, right? So removing states that cannot be reached is the first thing in the reduction process. So why we would certainly not create such inaccessible states on purpose? In the process of designing a complicated machine, certain states may be created, which are later bypassed by some improvement. And we may have noticed that they have become isolated and you cannot link any other states to them. So it's better we remove it. So most computer application contains significant section of dead codes, which are not really useful. So a state in a finite state is inaccessible. Now listen to the definition. A state in an FSA is inaccessible if there is no input string for which the machine will reach that state. A state in an FSA is inaccessible if there is no input string, like for instance, you have 0 leading to it, but 1, we can't get to it on the other input, for which the machine will reach that state. Moving on. So let's look at this state diagram. So we start using standard English now of automaton. So this is a state diagram. So consider the following FSA. Now we have that the initial state is what? Just unmute yourself and answer quickly. What's the initial state here?
E.
Good.
Yes, sir.
So how many accepting states do we have?
2.
Huh?
2, sir.
So how many states do we have?
6.
So those are the things that you should first of all know how to interpret by default. And I'm glad that at least we have all learned that in previous classes. So starting with the initial state A, we can reach the state B and also the black hole Z. Since the diagram has no arrow leading out of A with a 1 label. That's with a 1 label. Now look at the diagram. You see, this is the initial state. So you have 0 leading to a B. Now look at the same A. Is there any label of 1 leading out of A, getting to another state? No. So we call that a state called Z. So from state B, I think you should be verifying what we're saying so that you can be fast. So from state B, we can get to B and D. So when you look at state B here, when you look at state B, this state B, upon the receipt of 0, it comes to B, and upon the receipt of 1, it goes to where? D. Moving forward. So from state D, we can reach this state D. We can reach, this is 1. But for the other output, 0, is not leading anywhere, right? So let me clean. So from D, we can reach Z and A. So starting from A, the only state that can ever reach, that we can ever reach are what? A, B, D, and Z. The others C, E, and F are inaccessible and so can be deleted. So the systematic way of doing this is to prepare a list of accessible states. But first, it is a good idea to express the FSA in a state table. Now, we're going to be looking at what is here, what we have written here. We're going to explain it one after the other shortly, so that you can get a grasp of what this statement is. Now, if you look at the statement, what it's saying is this. Let me clean up this. Now you have from D. Now, okay, from A, at least you are following from the beginning. Say, starting from A, we can reach B, and there's no way to get to another state. We go to a black hole. There, from B, we can get to BD. From D, we can get to Z. So only A, B, C, D can be reached by just moving from each of these states that we can reach one after the other. Other states are inaccessible and so can be deleted. So let's look at how that can be done. I'm sure by now, all of you should be able to draw the state table here. Now, can you just try on your sheet of paper if you can come up with the state table of this? So you have 2 minutes to quickly do that. Let's see if you can come up with the truth table of this. So I may just call any of you to put it on your screen so that we'll see it. So you put on your video and you show us to be sure that you did the work. Yeah, quickly do that. So let me look for somebody to call. So Ademuyiwa Abdulbakir. Ademuyiwa Abdulbakir. Oh, am I correct? Yeah, so let's see what you have done. Yes, so you can put on your video and show us what you have practiced or what you have done so far. Just put it on your video, let's see. Can't see anything from you. Ademuyiwa, I can't see anything from you. Oh, you have not even done anything. Ademuyiwa, I'm still waiting for you now. I'm zooming from the frame. And I put on the PC of the individual now and show us what you have done. Oh, nothing to show. You are not even doing anything. You are playing, Abby. Put on your mic and speak. Let's hear what you have done. Put on the mic and speak. Yeah, so Ademuyiwa, I'm going to yank you off the class because you have refused to obey simple instructions. Put on your mic and speak. And you are just keeping us waiting unnecessarily. Ademola Muraina, you said, is it state? Yes, it's the state table. Yeah, do you have anything to show us? Ademola Abdul, oh no, Ademola Muraina. Yeah, can you unmute yourself? Ademola Muraina. Oh, just that's the name now.
Good afternoon, sir.
Yes, good afternoon.
Okay. I've drawn the state table, but I
Your network is breaking
show
up.
it.
You don't what? Just put on your video and put it on the video. Let's see what you have done.
Okay, sir.
Yeah, just put the document that you have done. Let's see what you have done so far. Just put it on the screen on your video. Let's see what you have done. Okay, so we can see your hand. Yes, we are just looking at your face now. Put the document and let's see what you have done so far. Okay. It's not well positioned, so we can't see clearly. Well, I think probably she disappeared or something, or probably there's a network issue. All right, so let's move on. Yeah, so Ademiwa, whatever, I expect your written document why you have refused to obey the instruction on the class. All right, so moving forward, so this is a state table. Now you will see that under 1, you have nothing to write because there's no input that can lead you to 1. Then you see under D for 0, or for D under 0, no input. Then for F, no input. Then if you look at it, how many accepting states? We have 2. So all accepting states are what? Giving the value of what? They are indicated using asterisk. So you see, excuse me, you see this indicating that this is an accepting state, this indicating that F is an accepting state. So when you look at here, there is no input. If you look at it, the states that are the diagram, here there's no input, and here also there is no input, right? So the next thing after drawing the table, which is this, is to introduce the inaccessible states. Which is Z, which also serves as the states with input. So it now becomes a state with input, right? So excuse me. So you have the new diagram to be A with this. So all states that we do not have any stuff leading to them will now be given the value of Z. And the Z, which has been introduced, also has a state, which is forced to remain at a place. So you remember the concept of the black hole. You have all diagrams going to it. and we still have any other one to force it to remain. So this is for 0, and this is for 1, and this is state Z. Okay. So this is the first thing. By now, I'm sure you know how to draw the diagram for the states table. Do I assume that you know how to draw the diagram for the state table, everyone?
Yes, sir.
All right. So in as much as you can draw that, you should also understand what I've done. I only introduced the inaccessible state, and the inaccessible state as its own independent state and the input. And you know that its input has to be forced to remain in that black hole. So for the transition of 0, it goes to Z. For transition of 1, it goes to Z, right? All right. So moving forward. Okay, Mr. Joseph, thank you. So we begin by writing down the initial states. Now, this is the process, so listen very carefully. We begin by writing down the initial states. In this case, A is our initial state, as you have rightly seen that A is our initial state. So the first thing we'll write is that we write out the value of A. So we'll bring it out, right? So even if it is not possible to ever return to that state, it's accessible simply because we start from there. So accessible, the initial state can never be said to be inaccessible, because that is where you will start all your calculation or all your logical reasoning from. So the first thing is that you write out the value of A. Now, the next thing is that having written A, so having written A, you look out for the input states of state A, then you write them out. So when you look at, let me go back. Now look at A. What are the input state of A? When you receive a 0, you go to where? B, and the other one goes to where? Inaccessibility. So look at this table now. The input state is what? B, Z. Moving forward, you have B and Z. So you have A here written out. Now, once you first of all write out A in this manner, first step, the next one is that A, as soon as you put something under A, it means that you have started writing the input, or you have started processing what A will lead us to. So you have, sorry, let me see clear. Yes, clear for drawing. So here. So you start with A, right? So the next one is to write A to begin your processes. So the input for A is what? B, Z. So if you now look at this, the next state you are seeing is what? Is B. Now, once you have written this, as this stroke under A means that you have processed A, right? So the next thing is you write A, B, Z. So you now look for what is the input combination of B, which is the next on the, okay, so let me see, you have A, you have B, and you have Z. So when you put this, means that you have dealt with A. So the next thing you are dealing with is what? A, B, right? Z. So this is B that you are dealing with currently. You have dealt with A, you are now dealing with B. What is the input combination of B, which is what? B, D. So what you have in all is that you have A, right? You have done with A, you have B. So B, the input combination of B is what? B, D, then you put the last guy here, Z. However, you have two B's using the law of Boolean algebra. So you just have B dot B equals to what? B. So you just choose one of that. So you have A, B, one B has gone. So you have D and Z. So you have done A, you have done B. So the next thing to deal with is what? D. So you bring it up here again. You have A, I hope you are following, A, B, D. You have done with A, you have done with B. The next one you are dealing with was D. So let's go back to the table and look at what is the value, the input combination of D. So I think it's here. What we have for D? D is what? ZA. If you go to the table, you have your BD to be what? ZA, right? ZA, then you bring out the last Z, which is here. You put your Z here. No problem. Let me show you the table so that you don't get. Now, look at this table here. This is D. So ZA, the Z we're dealing with before, you put Z here, then A. So that's where we came about the value of D being Z and A, right? So coming back here, this is where we are. So the next thing we look at, okay, is there any repetition? Of course, we have A and A. So we just pick one A to represent the lot. So you have A. We have factored in this A and A. The next one is B. There's no double B. The next one is D. There's no double D. Right? So we have Z. It's two. So we just choose one of it. So Z. So we have done with A, B, T, left with Z. So the next one dealing with Z, once we want to deal with Z, we write at A, B, D, and Z. So we are done with A, done with B, done with D, then Z. What is the output for Z? Is Z and Z. But we already have one Z, so these two can be eliminated. So all we have left is what? A, B, D, and Z. So, we wrote in an earlier discussion that we'll explain what all that means. So we say from D, we can reach Z. Okay, let me clean this whole thing so that you'll be able to see. Clear. So we say from D, we can reach Z and A. So starting from A, the only accessible state we can ever reach is A, B, D, Z. Have we proven that? Yes. The other C, E, and F are inaccessible and so can be deleted. So do you understand the process of removing inaccessible states now? Response. Do you understand the process of removing inaccessible states as we have done here? Response. Can you see hear me? Okay.
Yes, sir.
Okay, do you understand what I've explained so far?
Yes, sir.
Okay, what about others? So who does not understand? If you don't understand, raise up your hand so that we go over it again. But if you understand, then we assume that, yeah, peace, you can speak.
From the current slide, that's why I didn't really get.
That's where you didn't what?
I didn't really understand. I understand the first part about A, but from B.
Okay, so let's go over it again. So this is what I'm saying that now, okay, look at this diagram. I'm sure you know that this is the initial state, right? And this is an accepting state. This is an accepting state. And we have two accepting states. So the next first thing we do is to draw the diagram, right? So if you look at this diagram, is what we are trying to work with. So what we want to do is to remove the inaccessible state. So we begin by writing the initial state, which is, you know, that is being represented by this A. So here, you write out the initial states A. Yeah, you get that, right?
Yes, sir.
Okay, so when we write out the initial state A, then we look at, okay, what is the input combination for A? So let's go back. Look at, this is the input combination of A, which is what? B and what? Z. The combination of B is what? B and D. For C is what? F and B. For D is what? Z and A. For F, for E is what? B and D. For F is what? Z and E. For Z is what? Z and Z. Do you get that? All
Yes,
right.
sir.
So let me clean or clear all. So I said the first thing you do is to write the starting state, which is our what? Our A. So you write out your A. So what are the input combination for A? As shown earlier is what? B, Z. So you write out what? B, Z. Remember, you're supposed to write A first. Then you go to the next step by writing out the input combination of what? A. So as at the time you are writing the input combination of of A, you put a line underneath showing that it is being processed now. So from the table, you know where we got BZ from, right?
Yes, sir.
Okay, so once you have written BZ, you look, the first thing you look at, is there any repetition of letters so that we don't have double nodes? So there's no repetition. So you go to the next one, the next letter or the next state on the generated inputs. Now, it is not according to the table. Maybe you have A, B, C, D, E, F. No, it is according to what is generated. However, what is generated is also rearranged in order to reflect seriality or the order of being serial. So you have generated what? B and Z. So that means you have dealt with A, B, Z is what you have developed. So the next one is what? A, you are done with this. Then the next one is what? According to hierarchy is B, right? So you put on B, right? So what is the input combination for B on the table? Can you look at the table and tell us the input combination of the table?
B and D.
Is what? B and D. Do you see it now?
B and yes, sir.
B and D. So let's go back to, oh, sorry. Let's go back to this guy. So we have B and D. So B and D, you write them out. However, up here, you still have one guy hanging. So you bring it down as Z. So the next thing is that you now evaluate, are there repetition? Are they well arranged? So you see that this is A, B, D, Z, well arranged. However, we have double B. So using the law of Boolean algebra, when you have B dot B to be equals to what? B. So you bring in just one B. So you have A, B. So instead of writing another B, this has taken care of it. So you give us the reason why this one of these B is disappearing. Then D, right, and Z. So you put your arrow, that's your line under it, showing that A and B have been evaluated. So the next one is what? A, B, D. So what is the input of D from the table? From the table, what's the input of D?
Z and A.
Okay, so Z and A. So you bring in the value of what? Z and A. So that means you are processing D at this point. Now there's one of these guys still up here. So you put it as what? Z. So in a way, you could decide to arrange all of this to reflect seriality so that it will be easy for you to cancel out. So you can have A that has been processed with another A that is at the extreme. Then you have, sorry, this is not correct. So let me cancel it. Let me have the result. Okay. So you have A, which is being processed. Then you have another A that is just coming in, not processed. You have B that has been processed, right? Then you have D that is being processed. Then you have Z, Z. Do you understand what we have done? We just rearranged so that all those repetitions can come very close. So here, A dot A will give us just one A that has been processed. Then we have B processed. We have D processed. Then Z dot Z is what? Z. So the next one is what? That to be processed is what? Z. A, B, D, all these processed. Then Z that is being processed. What is the input for Z? It is just Z, Z. So you could just still take a Z dot Z equals to what? Z. So you have another Z again, Z dot Z is equals Z. So in all, in your conclusion, you have that A, B, D, and Z. So you can see there's no other input that we can generate from here. Hence, any other state after this is inaccessible. Do you get that now?
Yes, sir.
Okay. So do we still have any other person who has not got that? All right, so we move on. So I just use all these to explain, and I was still writing plenty English. So all you need to do is just to write out the initial state and start having the possible combination. So for now, there is nothing further to consider because we have exhausted all the combinations. So our list of accessible states is complete. All other states are inaccessible. So C, E, and F are inaccessible and may be removed. We can simply erase the corresponding rules from the table, and we have this. So what we have now? We have A, B, D, and Z. So the input for A is what? BZ. The next one is what? BD, and ZE, ZZ. And you put only one asterisk because F has gone, which is an accepting state. So you can delete an accepting state, but an initial state may not be deleted all of the time. So this is just removing the process of removing inaccessible states. So the next thing we are supposed to consider is what? Equivalent states. How do we look for equivalent states? So please pay close attention to this. So you have how many states here?
8.
8 states, good. How many accepting states?
3.
Three.
Okay, so what kind of FSA is this? According to our definition in the last class, that an FSA that has more than 2 accepting states is called what? Oh, you didn't pay attention to that. Yeah, who paid attention to that? Yeah. So an automator that computes a Boolean function is called an acceptor. All states, okay. So a classifier has more than 2 final states, and it gives a single output when it terminates. So what we have here is what in the former listing that I showed is what?
The classifier.
All right, it's a classifier, that's correct. All right, so moving forward, say look at the diagram below. We have been able to identify that we have how many accepting states? How many accepting states do we have?
3.
3, good. What's the initial state?
A.
A, all right. So moving on. Okay, so how do we now do the, how can we now determine if it is equivalent to another machine entirely? So that's the process we want to do. So the first thing is that you should be able to draw the truth table by now. Abi the participants, okay. I'm sure you should be able to draw the table by yourself now. Now, please verify to be certain that the first table is correct. So draw the state table. Verify that the table is correct from here. Is the state table correct? Sorry. Has anybody drawn the table? Yeah, can you quickly draw the table using this diagram quickly? Yeah, has anybody drawn the table? Nobody. Okay. But do you understand what has been done here? Do you understand what has been drawn, what has been shown here?
Yes, sir.
All right. So the next thing to do after drawing the state table is to identify the inaccessible state using asterisks. So the next one is what? Having the asterisks on the for the accepting state. So A, E, and H, they are what? They are the accepting state. So you indicate them what? Using asterisk. And you still remember that the asterisks are going to be changed to what? Figure 1, 1, 1, and all other states will be converted to what? 0, 0, 0, 0. So here we have to, in a way, convert them to what? 1 later. This one will be 0. This one will be 0. This one will be 0. This guy 1, 0, 0, 1. So you see all those guys with stars or asterisks are assigned the values of what? 1. And any other assign the values of 0. So this interpretation is what we know what we know as what? The zeroth equivalent. So when you change all these asterisks to 1 and any other states to 0, it is known as what? The zeroth equivalence. Do you understand? Do you understand up to this point? Or you don't understand what I've just explained? Or have I been thrown out of the class? Not really. Okay. So what I'm saying in essence is this. You understand why we put this as an asterisk, right? Why we put asterisk here is because they are accepting states. Okay. Let's look at the diagram again. States diagram. Now look at this guy. So you can see A is an accepting state, E is an accepting state, and H is an accepting state. So they should have the value of what? 1, 1, 1. But on the initial table, what do we put on them? We put star, asterisk, 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 to tell us that these are the accepting state. It's just a place marker telling us that these are accepting states. Do you get it now up to this point?
Yes.
So, okay. So moving forward now, I now say that once you have all that done, the next thing is you can now remove the place markers and say, okay, this is an asterisk, this is an asterisk, an asterisk, an asterisk. And anyone that has an asterisk will have what? The value of 1, as I explained earlier in the last class. This we have the value of 1. Right? So this will now be removed. This will be removed. This will be removed, telling us that what? A is an accepting state, E is an accepting state, H is an accepting state. Okay, maybe if I move to the next state, the next page, you will understand. So, will you log a table with as many rows as original table, but with many columns? So we copy the states and the transition table into this larger table, and then copy the accepting state column into the next column. Now, this is what I was trying to explain. You can see that we said A is what? An accepting state. In the former state, it was having what? An asterisk. E was having an asterisk, right? And H was having an asterisk. Do you understand? Hello.
Yes, sir.
Yeah, so what I'm saying in essence is that once you bring that here, all right, so once you get to this point, instead of having your asterisk here, you just replace your asterisk with what? 1. Asterisk with what? 1. Asterisk with 1. And any other state will become what? 0, 0, 0, 0, 0, as you have seen. So let me go back to the previous one so that you look at it. Look at this guy here. This one has what? An asterisk. It has now been replaced with what? 1. This guy has an asterisk. It has been replaced with 1. This one has an asterisk. It has been replaced with what? 1. So every other state is what? Assigned the value of 0 because of what? They are not accepting states. Do you get it now?
Yes.
Okay. So, okay, so Ajayi Emmanuel, do you understand now?
Yes, sir.
Okay, so let's go forward. So please pay very close attention as we move on now. These are very delicate times. So once you are done with all this, then we call something called zeroth equivalence. We want to check that, okay, is this the diagram that we have, this is the first stage of equivalence, the zeroth state of equivalence. That is the base case of its conversion. So once you have just changed the accepting states and the non-accepting states, you have represented with what? 1 and zeros. You label it as what? Your zeroth equivalence. This is the inputs. This is what? These are the states. These are the states. Right? And this is the initial states. These are all states, 8 states. Then accepting states, accepting states, accepting states. So that is the what? Initial states. This is the initial state, and this is the zeroth equivalence. So the next one is now to generate the next set of inputs. So the next set of inputs, you now generate what? Oh, sorry, let me clear this one first. So you now have, sorry, clear. So you have 0 and you have 1. We want to generate what? The first equivalence, which is written as this. So how can we generate that? Please listen very carefully. You have been able to generate what? Your zeroth equivalence. So the input combination will now be assigned this value. So look at what I'm going to do. You bring all these zeroth equivalence here and you put the value in front of all this. This is 1. This is 0. This is what? 0. This is what? 0. This is 1. This is 0. This is 0. And this is 1. All I did is just to have all this put in front of this likely. It's not that it should be there, but for the purpose of explanation. So what we are saying is that this A is an accepting state, has value of 1, right? E is an accepting state. H is an accepting state. All other states are assigned 0. It is with these new found values of A, B, C that you now generate these next values. So here, anywhere we see A in this input combination, we put A to be equals to what? 1, B to be equals to 0, C to be equals to 0, D to be equals to 0, E equals 1, F equals 0, G equals 0, H equals 1. So let's start. The first combination that we have is what? A. What are the input combination of A? We have what? B and D. Are you following, please?
Yes, sir.
Okay, do you all understand up to this point? Okay, I think you should all start participating now so that I will know you are there. So if you understand up to this point, can you just raise up your hand? So you need to be very fast when I'm asking questions. Raise up your hand quickly, quickly, quickly. If you don't raise up your hand, I will yank you out of the class. That means you are just somewhere else. So Adeniji, you're in traffic, Abi. So we expect that all others did not understand. So I think we should just remove them out of the class if they don't understand. Yeah, I didn't say you should type. I say raise up your hand if you understand. So if you don't understand, so that we know how to remove you from the class. You have just been wasting our time. So Adibola Tolulope, you don't understand. Adigoke, Oluwadami Larry, Ajeni Fuja Samad, you don't understand. Akambi Usman, Akinjide Oluwa Yemi, Akambi Usman, Akinyemi Olatunbosun, Alade Michael, Anjola Jesu, Abi Anjola Oluwa, Ote something, Atun Rashi Ayomide. So all others don't understand. Okay, so drop your hand. So let's see how many will not understand. If you don't understand, all of you drop your hands quickly. We have taken a snapshot of those who understood the process. Drop your hand quickly, drop your hand quickly. Daramola Muraina, drop your hand. Ubanga Fama, Biunfawa, peace, drop your hand. Peace, drop your hand. Okay, so if you don't understand, raise up your hand, please. If you don't understand, raise up your hand. This one doing double twirling. Okay. So just 2 people. So what about the others? They didn't attend the class. If you don't understand, raise up your hand, please. Okay, so just 2 people. Don't worry. So I'm going to start removing all of you from the class now. So let's go back to the class. Now, let me clear and start all over again. Clear all the backgrounds. Now, do we understand up to this point what we have done? Do we understand up to this point, please? Okay. Yeah, for those of you who raise up your hand that you don't understand, you better respond very fast. So, all right. So, you know we generated the 0 to equivalence. So what I'm saying is this. You have this equivalence here, or this. So all you will do is to just move it to this place. To say that, okay, at this point, you say, okay, let me just write it here. You say A now takes up the value of what? 1. B takes up the value of what? 0. C takes up the value of 0. D takes up the value of 0. E is an accepting state, so it takes up what? 1. F takes up the value of what? 0. G equals to 0. And what? H equals what? 1. because it is an accepting state. Yeah, I hope you are all following. So you now want to generate the next set of inputs on this to generate what? This is zero to equivalent. You want to generate the first equivalence. So what will you do? You have 0, 1 here. So you bring it here as 0, 1. It's just this combination of states. At the first instance, you have that once you're at A, you receive a 0, you move to B. Once you're at A, you receive a 1, you move to D. But now, B has taken up a new value. And what's the new value of B? Equals to what? 0. The new value of D what? Equals to 0, giving this 0 to equivalence. Do you get what I've just explained? Or do I run it again? Now you have A. Okay, let me just generate so that we don't remain in this black hole for too long. So you have A going to B, D. So to generate the same thing here under this new arrangement, because it's going to change, we are trying to develop an equivalent system that will be like this initial diagram we have drawn. So we have A, which is what? B, D. Now here, we know that A is going from where? He has under 0 goes to B, under 0 goes to B, under 1 goes to D. So to replicate this here, we have that our B is what? Having the value of 0. Our D is having the value of 0 under this new arrangement. B goes to E and D. E is what? An accepting state 1. D is what? Is 0. F is 0. B is 0. E is an accepting state. B is 0. F is 0. G is 0. H is an accepting state 1. G equals what? 0. H is an accepting state. F equals 0. D equals 0. C equals 0. So if you look at it here, B here is what? 0, which is here. D equals 0, and it is here. Do you understand what I've done here now? Oh, that's good. So that's what I was trying to put out there, that okay, we want to generate a new machine that can be like this one that is here first, that is here, this guy. So, but we have changed the values of A to be equals to 1, B to be equals to this, and C equals to this. So this is how we generate the next one. So the next thing we are going to generate is what? The first equivalence. That's a new machine, which is this. So how do we generate the first equivalence? Now look at it. You will be looking at patterns, right? So the patterns is like this. These patterns like this. These 3 columns, right, is what you'll be looking at as your pattern. Do you see it? You'll be looking at those patterns, these 3. Or you look at them at the same time. So they form a pattern. So what pattern has this guy formed now? If you look at it critically, it forms a pattern of what? 1, 0, 0. 1, 0, 0, right? Are you still following?
Yes.
So it's generating a pattern of 1, 0, 0. This is generating a pattern of what? 0, 1, 0. This one is generating a pattern of what? 0, 0, 0. The next one is what? 0, 1, 0. And it goes down like that. However, remember, that when we add B dot B, we just said equals to what? B. So in essence, any of these combinations that are the same, giving the same value or the same numbers. So how do we now go about it here? So what we do is that for every pattern we come across, the first pattern we come across will be given the value of what? 0. The next value that will come across will get the value of 1. But if we have a repetition of what 0 has represented, we give that same place the value of 0. So let's look at it here. We have what? 1, 0, 0. We give the value of what? 0, because that's the first thing we are coming across under equivalence 1. Then we'll now go, we scan down the columns and we see have any value that is what? 1, 0, 0. So you look at this E, it has a value of what? 1, 0, 0. So you still give it the same value of what? 0. We have H to be what? 1, 0, 0. You give it the value of what? 0. Then we have been able to sort out all the similar patterns. So you can see 1, 0, 0, 1, 0, 0, 1, 0, 0. So they are similar. So we give them the same value. We start numbering, as I said, from 0, 1, 2, 3, 4, 5, 6, 7, 8, like that. The next one is, we'll go to the next one, which is B. B is different from A. So we have what? 0, 1, 0. We'll give it the value of what? 1. So do we have any other station, any other state that has 1, 0, 1, 0? Let's look down. We have this T. So we'll give it the same value of 1. Here, we'll give it the same value of 1. Here, we'll give it the same value of 1. Right? So that means we are dealt with that. The next one is C. C has a 0, 0, 0. We give the value of what? 2. Is there any other one that has 0, 0, 0? No. So we are done with our zeroth equivalence. So do you understand how we got this zeroth, the first equivalence?
Yes.
Yes, sir.
Okay, so let me see. All right, so thank God it's quite easy. Now, you will now look at the, okay, good. So we'll now look at another way. Okay. So you now compare this guy, this zeroth equivalent, and the first equivalence. You compare their outputs. That are they the same? So you look at 1, 0. Obviously, they are not the same. Once there's a change, if you have 1, let's say this is 1, this is 1, this is 0, 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 1, 1, 0, 1, 0, 0, 0, then we say they are equivalent. But if you just have a slight change, right? So this is 1, this is 0. So what we expect is that we go to the next, we generate another machine and test if it's going to be the same as the previous one. So the next one is that we generate the next set. Now, you know this guy now, when we're having zeroth equivalence, the value of A was changed to this, the value of B was changed to this. But now, what we now have is this. Sorry, I should have canceled that. So you have your B and you have your A. So the value of A will now take these values under equivalence 1. So the value of A will now become what? 0. The value of B will become what? 1. The value of C, 2. The value of D, 1. The value of E, 0. The value of F, 1. The value of G, 1. The value of H, 0. Do you understand what I've done now? Do you understand what I have done?
Yes. Yes, sir.
Okay, all right. Do we still have a few people who understand, or just one person? So if you understand what I've done, please can you raise up your hand quickly so that we know that you're not just one person. If you understand what I've done, okay. 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 So do we have one email that, oh, good. So we have almost 13 people. So that's a great number considering the sample population. All right, so you can drop your hand now. Thank you for your feedback. So let's now generate the next combination of inputs. So now you have B and D here. So represent B and D here. We have B to be equals what? 1. And D equals what? 1. Right? The next one is that ED. Our E equals what? 0. And our D equals 1. The next one is what? CF. Abi FB. What is our F? 1. What is our B? 1. The next one is what? EB. E equals what? 0. B equals 1. The next one is FG. FG is equals to what? 1 and 1. HG, we have 0, 1. HF, 0, 1. DC, this is what? 0. No, this is 1. So D is what? 1. And C is what? 2. Do you all understand up to this point?
Yes.
Yes, sir.
Okay, so the next one will now still generate the what? The second equivalence. So let me quickly clean up this. So we generate the second equivalence. So how do we generate the second equivalence? It's just as we did for the first one. We look at from this point, right? All these points, we look at them together in group, right? So that's what we'll be doing. So let's look at the first one. We have 0, 1, 1. We give it the value of what? 0. So we now go down again. Do we have any 0, 1, 1? Yes, we have this 0, 1, 1. We'll give it the value of what? 0. Is there any other 0, 1, 1? None. So the next one is what? 1, 0, 1. We'll give it the value of 1. Is there any other 1, 0, 1? Yes, this is what? 1. 1, 0, 1, 1. 1, 0, 1, 1. Then the next one, we have another set, which is 2. Is there any other one? No. Then another one, which is 3. So let's compare the previous equivalence, which is equivalence E1 and equivalence E2. So 0, 0, good. 1, 1, good. 2, 2, good. 1, 1, good. 0, 0, good. 1, 1, good. 1, 1, good. 0, 3. So in as much as there's a discrepancy between these 3 and this, we go to the next equivalence. So we now generate the next equivalence again. So with that, let me go to the notes we get. So let me clear all this stuff. Clear all. So this is just a form of explanation. So the next column gives 0 to equivalent partition 1 for accepting state and 0 for non-accepting states, denoted by E0. Now then fill the other columns by looking for the combination of each input, starting from input 0 and 1. Assign them the values they now assume from the 0 to equivalent. Fill this new column combination under the new possible inputs, the 0 equivalent, and these new input values column forms a pattern to generate the first equivalence. Of course, I've explained that these 3 columns starting from the first set of input pattern forms the first equivalence row in order of encounter. Label this column starting from 0 until the last pattern is exhausted. That's what we have done in the previous slide. Then we scan those columns together with E1's column itself to get the equivalence 2 column. We continue in this way until we get 2 successive EK, which is just an arbitrary number column, being identical. Now look at the word successive. That means they must follow. You don't compare third equivalent with 0th equivalent. It should be 0 with 1, 1 with 2, 2 with 3, 3 with 4, right? And it goes on and on like that. So state B and D, okay, I think let's move on before we come back to this one. So, well, I think some of you are already tired and you are thanking God that the class has ended. But unfortunately, class has just started. So this is where we have gone through already, right? We have generated all this. We have generated all this. So you understand how we came about E1 and generated up to E2 like that. So you can see just giving them values as they come. So now this is our E2. So you understand how we generated this, how we generate the next input value by giving the value of E2 to A, B, C, D, E, F like that. We generate the next set. We look at all this together, right? And we generate it. So by the time you get to E4 and E5, that's equivalent 4 and 5. You see that 0 and 0 is the same, 1 and 1 is the same, 2 and 2, 1 and 1, 3 and 3, 4 and 4, 5 and 5, 4 and 5, 4 and 4, 5 and 5. So at this point, we say that these two machines are equivalent. So that's the process of generating equivalence, right? So the reduction process, how do we go about the reduction process? So the you identify the states. Now, please pay close at, okay, let me even ask, do you understand how we got up to this point, please? And what we did before we move on? Of course, just repeating what we have done from zero to equivalence, first equivalence, second, third, like that. All you'll be doing is just be comparing. You compare 3 and 4, you compare 2 and 3, 3 and 4. So once you just see that they are the same at that point, then you can stop, right? Do we understand up to this point? Okay, so 2 people. Okay, good. Oh, that's good. At least we have a number of people who understand. So good. So the next one is the reduction process. So to identify 2 equivalent states S and T, we select one of them, say S. There represent them both, and redirect all references to T to a reference to S. So example. Now we have been able to look at the past this here. Look at E4 and E5. Please pay close attention here. You have E4 and E5. So we see that this is 0 and there's no other 0. So this stands on its own. This is 1. This is another 1, right? So the first one that you encounter, we take precedent, and this state we die, will be cancelled out immediately. We only take the first one. The next one, we have 2. Is there any other 2? No. Here, we have 3. Is there another 3? No. So this one remains alive. This one remains alive. This one remains alive. But you have 4 and 4. So the second 4 dies off. Then we have 5. So this one remains alive. So what we do is that whenever we see, please listen carefully. Whenever you see 1, or whenever you see B now, which is representing the first one we encounter. For instance, here you have B. Then D is dead, or has been removed. Let me not say dead, has been removed. So you see this input combination, you have E and D. In as much as D has been removed completely, what we do is to put what has replaced it, which is what? B. You can see B is taking the lion's share because we came across it first. So it's going to take up this value. Now look at this one, B, D. You have B still alive, D has been removed. So here you put what? B. Now look at the other one. You have F and G. So you have F here. F is still alive. G has been removed. So here you put F instead of G because you are going to cut out D. You are going to cut out G. Let's look at this is H. H is still alive. You leave H. You have G, and what is taking over G? So it is still F. So let's look at how that can be done, so that at least you can understand what I've just explained generally. So clear on. So look at this. This is the same diagram that we looked at earlier. The state table that we're looking at. This is where we started from, where we said A, E, and H, they are accepting state, and we recognize them with asterisks. So now, and we identified that some of these points are about to change. Okay, let's label it again so that you can understand this. So you see that, okay, somebody's writing. Is it only when we reach the 5th equivalence we can replace the states? No, it is when the successive states, if they are the same, if they have the same value 0, 0, 1, 1, 2, 2, 1, 1, 3, 3, that you can stop. It may go up to 18th equivalent. It doesn't have to be 5th. You can even stop at 2 and they are just the same. So at that point you stop, not at the 5th. It's not usually at the 5th. Put that, please note that. You could have up to 100th equivalent, right? It's not just on the 5th one. So let's look at this. Now, look at this diagram here. You have that A is on its own. Just be looking at the comparisons that I'm going here. You can see A still exists, right? Because, okay, how do I? All right, let me do it this way. A here is what? Is A is 0. So let me just label it so that we can have a good understanding of what we are saying. A here is what? A is 0. So A notation. So A is 0. I'm looking at the last equivalent. I'm trying to bring it forth and back. So B is 1. So C is 2. So here is 1, 2. And this other one is what? Still 1. Okay. And the next is what? Oh. Okay, so here is what? 0, 1, 2, 1. So 3, 4, 4, 5. 3, 4, 4, 5. 3, 4, 4, 5. Now you can see the malady in this diagram here. You see that A equals 0, B, C, then you have B. But what ought to be here was what? D. But because B is 1 and D is 1, we say that B takes the value of what? D. So we'll put D here. You see this guy too, 3 is on his own, 4, which is F. After F is what? Should be G. But you see F and F. Why? Because F is the first to be encountered that has a precedence over the next 4 that we're going to encounter, right? So we have F, F, then H. So instead of A, B, C, D, E, F, then G, H. When we look at the early diagrams we have, we saw that in the 5th equivalence, we saw that in the pattern, 1 that we came across, then this guy. So this guy, D, we die or we go, and B, we take over the values or the function of this. Then F, we came across F to be 4, then G, we go. Now, let's assume that C is 2, and let's assume that H is also 2. So what we have is that C, we take the value, we take the position of H, then H, we go. And anything pointing at C here, which is this. So what's our C? Okay, so this stands B and C. I don't know if you get what I've just explained. Hello? Am I still in class? Does anybody understand what I've just explained? Oh, that's strange. No, okay. Let me go back and explain again. All right, so let's see. Clear on. Clear on. Okay. So let's look at this. Now, do you understand up to this point? Yeah, let's have responses quickly. Do you understand how we got to this point? Okay, so now let's now look at it critically. What I'm saying is this. You see this E, this equivalent 4, equivalent 5. You can see they look alike in their outputs. 0, 0. You can see 0, 0, 1, 1, 2, 2, 1, 1, 1, 3, 3, 3, 4, 4, 4, 4, 5, 5. Do you see them? Can you see that? But when you compare this equivalence 2 and equivalence 3, now when you look at, you have 0, 0, they match, 1, 1, they match, 2, 2 matching, 1, 1 matching, 0, 0 matching. But you can see a difference, 1 and 3. As soon as you see a difference, that means they are not the same in their outputs. So you go to the next one, and that's what happened for us to go to equivalence 4 and equivalence 5. But when we got to equivalence 4 and 5, when we looked at the successive one, we found out that equivalent 4 and equivalent 5, they are the same in their outputs. Do you understand up to that point? Response? Do you understand what I've just explained now? That 0 equivalent to 0, 1 equivalent to 1, and all that. Okay. Oh, that's better. Now look at the next explanation now. The next explanation is this, that you have the patterns that you have looked at. This is 0, right? This is 1. This is 2. This is another 1. That means when you look at this 3, 1, 3, 1, they have the same input and output value. So what we are saying is that the first one is what? B, right? Which has the first value of 1. The next value of 1 is what? D. Are you still with me here? Do you understand what I've just said? You have this guy, B, having the value of 1 because of the combination. Then you have D, having the value of 1 because of the combination. Okay. Now, what you do is that the first person you come across, which is B, will take over the function of D. So what will happen is that wherever you see B, you replace it with what? Wherever you see D, you replace it with B, because B has taken over the properties and the value of D. Do you get that explanation, or do I repeat? Okay. Any other response? You get what I've just explained? Okay, that's 3. Many more. 4. Okay. I need about 10 people. If 10 people understand, that's okay. 5. Five is not a good number. All right, let me explain again. Here's what I'm saying. It's clear. I want to clear all that. Now, I said when you have generated this guy here, and you also generate this guy, and you understand how we came about this generation, you look at this pattern 0, 1, 1. That's the first one we are coming across. We give it the value of 0. The next one is, so we now look down. Do we have any pattern that is 0, 1, 1? None in this columns, these 3 columns. The next one is what? 1, which is 1, 3, 1. Do we have any other one that is 1, 3, 1, which is this? D. Now, when we have generated all of this now, we now come to check if equivalent 4 and equivalent 5, if they are the same, and we have established that they are the same. So we now want to, in a way, do a reduction so that we don't have states that have the same function being repeated. We want to remove redundant states that their duties can be performed by another person. Now look at, let me clear first. Now look at this one, 0. Is there any other 0 in this column? No. But look at this guy, 1. Is there any other 1? This is another 1. 2. Is there any other 2? No. 3. Is there any other 3? No. But 4 has another 4 here. In order to reduce it, we will remove one of the states that have the same number. So you have 1, 1 here, and you have 4, 4. How do we now remove it? The first number, or the first state that we meet, we take precedence over the next state that is being repeated. So here we have B as the state, the first state we have met. taking precedence over D. Do you get that? Then you have F taking precedence over what? G. Do you get it up to this point? I want response quickly, quick. Okay, 3 people. Okay, 4. 6. Not really. Who is this fellow? Olukolatimi David. Okay, please put on your mic, Olukolatimi, and explain what you don't understand. Yeah, Olukolatimi, I'm expecting your response quickly. Put on your mic. Yeah, you can put on your mic now. Oh, you can't talk where you are and you don't understand. Okay, then you keep quiet. If you meet your mate and understand. How would you be in somewhere you can't talk and you are supposed to be in class? All right. So you have B here. So B is the first. So you have A with no repetition, right? Now you have B being the first to be considered. Then it will now take up the value of what? D. So we'll cancel out D and B will take over because they have the same inputs, the same input sets. Then C is still alive because there's no other repetition. Then E is still here, no repetition. Now, when we get to F, there's a repetition on G. So we take the first one, which is F, and we still take F again to represent this value of G. Then 5, which is H. So you can see A, B, C, then B, E, F, F, H. So you see the other diagram that was drawn. This is how we arrive at it. Anyone that we come across first, we take precedence over the next one, which is this. Now we have this one taking precedence over this because they are the same. So this will be taken and this will be removed. So let me clear on screen. So that's where we came across this diagram here. So we have A, B, C. Then in as much as B came first, we have B here again. E, then F, as I've explained earlier. So what you will do in essence is to just remove those, let me see. Oh, sorry. Yeah. So all you will do is to remove the repeated states, which is A, B, C. You know, D was repeated, it has been removed. E, F, G has been removed. Now, when we now go back and see the repeated states, here, you have A, B, D. Now, remember that you had removed B. You have removed D here because of the repetition. So when you now come back to all these diagrams, B, this should be D. But because D has been removed, instead of writing D that was here before, you now replace it with B. So anywhere there's B before on this table will be replaced with what? Anywhere there's D, you replace it with B. So look at, let's go back to the initial diagram. Now you see here now, here will be replaced with what? B. Here will be replaced with B. Is there any other D? Here will be replaced with B. Now the other one that was removed is G. You look around again. Is there anywhere there's G? G will be taken over by F. F. Is there any other G? So that is the whole essence that I was trying to explain. I hope you understand now. So that is where we arrived at this, and by the time we remove those repetitive states, we arrive at this. So he said we omit all repeated rules, and we arrive at this. So the next one is a standard form. Yeah, I think we could have the class ended now, so that some of you, class rep.
Yes, sir.
Yeah, so you have this is standard form, right?
Yes, sir.
So next week we start here on standard form. I'm sure
Okay,
most
sir.
of you will be at home then. So I want us to quickly get through with all this so that we can continue with converting to NFA, from NFA to DFA. So that once we just resume, all we have to do is just you continue with Dr. Senaike. Yeah, so all of you could put in your name and matric number. So put in your name and matric number. And if I check and the name and the username doesn't match, means you didn't attend the class. It's as simple as that. And for those of who perpetually join the class late, I will not tolerate that from next week. Once I start, I lock the class and you'll not be able to get in. And that's your business. Should be on the group before the time allocated. Olabi, you don't have a matric number, right? Joseph Olu, Ola Yanju. What's the meaning of M that you have written there? Yeah, this Chinaza and Ernest, the next time if you are joining, if you don't put your surname, I'm going to yank you off. You have always joined with Chinaza. You should put your surname.
No, that's just attendance. That's not even the problem. Probably like I cannot teach. Attendance. These are finished 2. That finished to 3. Never mind. Never mind. I think we'll go on. They are saying the extra hour that you get. Okay, because they will put it down. Oh, what's in it? Come on now. Oh. Well, not to